Dear students, today we are discussing 5th semester course subject linear algebra, that is chapter name is vector space and subspaces. Contents, objectives, introduction, vector space, subspaces, worked out exercises, check your progress, model examination questions and summary, etc. Next, objectives: define the concept of a vector space over a field, quote certain examples, prove certain important elementary properties of vector spaces. Third one, define the notion of subspaces of vector spaces and quote certain examples of subspaces. Next, introduction. The notion of vector space, linear space, originated from coordinate geometry as also formed from ideas of force and velocity. What is velocity? The rate of change in displacement is called velocity, that occurs in physics. Today, vectors and vector space plays a vital role. Means pivotal role means most important role in branch of mathematics, physics and engineering. Vector spaces. We shall make formal definition of a vector space and give certain examples and prove some elementary process, etc. Next, definition. Let F be a field. A non-empty set V is said to be vector space over the field F if there is a binary operation addition plus on V for all A belongs to F means field and X belongs to V means vector space. There is defined an element denoted by Ax in V. V means vector space satisfying the following. First condition, V comma plus. V comma plus is a abelian group. Abelian. What is abelian group? Abelian group also known as commutative property, commutative group. If satisfies the commutative property. What is commutative property? A into B equal to B into A. Second property, A into x plus y equal to Ax plus Ay for all x comma y belongs to V. V means vector space. A belongs to F. F is a field. Third property, A plus B into x equal to Ax plus Bx for all A comma B belongs to F and x belongs to V. Fourth property, AB into x equal to A within the bracket Bx for all A comma B belongs to V. A comma B belongs to F. F means field. X belongs to V. V is a vector space. Fifth property, I into x equal to x, where x belongs to V. I is a multiplicative identity in F. Note that in 3 above addition on the left side is that in F, while plus on the right side it is that in V. Also in 4, above the product A B on left side is that in F. The map F cross V, map means function, nothing but mapping is nothing but function. The map F cross V into V taking A comma x onto Ax is called the scalar multiplication. Is called the scalar multiplication. The elementary of F are called scalars. By the letters we are denoted A comma B comma C such that and the vectors denoted by x comma y comma z, so on. The operation addition on V is called vector addition and plus is on F is called the scalar addition. The identity element with respect to addition in V or in F is called the 0 vector, denoted by 0. The inverse of x and A in V or F respectively is denoted by minus x or minus a. Example, the set of real numbers R form a vector space over itself. What is R? R is the set of real numbers. Second one, R is a vector space over the set of rational numbers Q. Third one, Q is a vector space over over Q. What is Q? Q is a set of rational numbers. Now, theorem, let V be vector space over the field F comma F, x belongs to V and A belongs to F, then the following conditions are hold. First condition, what is the first condition? A into 0 equal to 0. Second condition, 0 into x bar equal to 0. Third condition, minus A x bar equal to minus of A x bar, that equal to A of minus x bar. Fourth condition, A x bar equal to 0, that implies A equal to 0 or x equal to 0. One more, x bar equal to x. Proof of the theorem. First condition, A into 0 plus A into 0 plus A into 0, that equal to, take A is common within the bracket 0 plus 0, 0 plus 0 is 0, that equal to A into 0 equal to 0. By the cancellation law in V, we get A into 0 equal to 0. Second one, similar to that of one, we will prove this condition further. So, third condition, 0 equal to 0 x bar, that equal to in place of 0 we are writing A minus A x bar, that can be written as A x plus of minus A x, and therefore, minus A x that equal to minus of A x. Also 0 equal to here 0 equal to A into 0, that equal to in place of 0 x minus x we are writing. So, A x plus A of minus x, and therefore, A of minus x is minus A x. Fourth condition, suppose A x bar equal to 0 and A is not equal to 0, then since F is a field, F is a field, A is the multiplicative inverse of A dash, and x equal to 1 into x, that equal to A into A inverse into x, that equal to A inverse into A x, that equal to A inverse into 0, that equal to 0, hence proved. Example, let K be a field and F be subfield of K, then K is a vector space over F. Addition in the plus is addition in the field K, and for any A belongs to F, F is a field and x belongs to K. A x is the product of A and x, and both are treated elements of K. The axioms 2 and 3 are simply distributive law in field K property. What is distributive law? A into B plus C within the bracket, that can be written as equal to A into B plus A into C. Fourth one is associative of multiplicative in K. What is the associative law? A within the bracket B C equal to within the bracket A B, that equal to C, that is known as multiplicative associative law. Fifth one is nothing but saying that the multiplicative identity in F is same as that in K. Thus, K is vector space over F. In particular, any field F is vector space over itself. Next example, let F be any field and n is positive integer, F n be set of ordered n tuples of elements of F. What is n tuples? N tuples means nothing but ordered pairs like that x 1 comma y 1, x 2 comma y 2, etc., x n comma y n. Those are all called n tuples of elements of F. So, here f n equal to a 1 comma a 2 comma etc., a n such that a I belongs to F for all I lies between 1 and n, means that can be written as 1 less than or equal to I less than or equal to n. If x equal to a 1 comma a 2 etc., a n and y equal to b 1 comma b 2 comma etc., b n belongs to f n and a belongs to F. Define x plus y equal to a 1 comma A2 B A2 comma etc. An plus B1 comma B2 comma so on Bn. Ax equal to Aa1 comma Aa2 comma so on Aan. Then with respect to these operations is a vector space over F. Next example, let X be a non-empty set, let X be a non-empty set and F be a field, let F dash be the set of all mappings, mappings means functions of X into F for any F comma G, for any F comma G belongs to F dash and A belongs to F. Define F plus G within the bracket X, it can be written as F of X plus G of X and A into F of X, AF of X equal to A outside, because A is the scalar F of X for all X belongs to capital X, X belongs to capital. Then with respect to these operations, F dash vector space over F, F dash is vector space over F. Next, subspace. If V is a vector space over a field F and W is subset of V, which is vector space over the field F with respect to the same operations in V, then W is called vector subspace of V. The following and equivalent formulations of the concept of subspace. Definition: let V be the vector space, let V be the vector space over a field F. A non-empty subset W of V is called subspace of V if the following are satisfied. Here observe, dear students, what is W also a vector space, the same conditions will apply for V. So, here W is subset or what is the difference? W is the subset of V, subset are equal to V. Then we will say W is the subspace of V, satisfy the condition. What are the condition? First condition, X comma Y belongs to W, if and only if X plus Y belongs to W. Second, X belongs to W and A belongs to F, that implies Ax belongs to W. It can be easily verified that non-empty subset of W of V is a subspace if and only if X comma Y belongs to W and A comma B belongs to F, that implies Ax plus By belongs to W. Note the abelian group, the abelian of group of subspace of vector space. Already we discussed what is abelian group. Means vector space, abelian group is nothing but commutative group. V is a necessarily subgroup of abelian group of V plus. Check your progress. That condition we said in the second condition, that we will prove here. Prove that 0 x bar equal to 0, proof 0 into x plus 0 into x. In these two, you take x common, 0 plus 0, 0 plus 0 is 0, 0 into x is 0 and hence by the cancellation law for addition in vector space, we get that 0 x equal to 0 if Ax equal to Bx, then A minus Bx equal to Ax plus of minus Bx, that equal to Ax minus Bx equal to 0 and hence hence A minus B equal to 0 or x equal to 0 if you took common or x equal to 0, Ax equal to Ay, that implies if you took A common, x minus y equal to 0, that implies A equal to 0 or x minus y equal to 0, hence proved. Example, let F and L be fields of the F and B subfields of the field K such that F is subset are equal to L is subset are equal to K is a vector space over F and L is subspace of K. F and L is subspace of K. Next example, let n be positive integer and F n be the set of all ordered n tuples. N tuples means already a1 comma b1, a2 comma b2, etc. n tuples of elements of a field f. Then Fn is vector space over F for any j lies between 1 and n, that can be written as 1 less than or equal to j less than or equal to n. Let Wj equal to a1 comma within the set a1 comma a2 comma etc. an belongs to Fn. Fn such that aj equal to 0 for all I is not equal to j. Then Wj is subspace over R. Theorem, let V be vector space over a field F, let V be a vector space over a field F, then the intersection any class of subspace of V is again a subspace of V. So, let W alpha, where alpha belongs to delta, be a class of subspace of V, and W equal to intersection x belongs to delta, since each W alpha contains a 0, W alpha also contains 0, and hence intersection alpha belongs to delta is a non-empty subset of V. X comma y belongs to intersection alpha belongs to delta and a comma b belongs to F. That implies Ax plus By belongs to W alpha for all. Therefore, W alpha is a subspace. That implies Ax plus By belongs to intersection x belongs to delta, and hence intersection x belongs to delta, W alpha is a subspace of V. C by P means check your progress. Theorem, prove that union of subspace of vector space need not be a subspace. Need not be a subspace. Here W1 here W1 equal to a comma b belongs such that a comma b belongs to R, and W2 equal to then a equal to b. W2 equal to a comma b belongs to R such that a is a equal to minus b, which is a vector over R. Here W1 union W2 is not a subspace over R. For example, W1 equal to 1 comma 1 belongs to W1 and 1 comma minus 1 belongs to W2, and hence W1 1 comma 1 and 1 comma minus 1 belongs to W1 union W2, and 1 comma 1 plus 1 comma minus 1 equal to 2 comma 0 does not belongs to W1 union W2, hence proved. So, definition, let V be a vector space over a field F and S is subset are equal to V. Define L of S equal to A1 x 1 plus A2 x 2 plus so on A n x n such that x belongs to S and A belongs to F and n belongs to Z. Here what is Z? Z is a set of integers. What are the integers? Both positive, negative together with 0 is called integers. So, L of S is called the linear span of S in V. So, theorem based upon definition, we are proving one most important theorem. This is let V be a vector space, let V be a vector space over a field F, then for S is subset are equal to V, the linear span L of S is a subspace of V and satisfying the following. First condition, S is subset are equal to L of S. 2. For any subspace W of V, S is subset are equal to W. If and only if L of S is subset are equal to W. Third one, L of S equal to S. If and only if S is subspace of V. 4. L of S equal to L of S. Thus, in sets A complement whole complement equal to A, we will write now the same way here L of S equal to L of S. Fifth condition, S is subset are equal to T, that implies L of S subset are equal to L of T for any subsets S and T of V. Proof, we have L of S equal to A1 x 1 plus A2 x2 plus so on an xn, and x belongs to S, A belongs to F. By taking A equal to 0, we can observe that 0 belongs to L of S is non-empty subset of V if x comma y belongs to L of S and x equal to A1 x1 plus A2 x2 plus so on an xn, y equal to B1 y1 plus B2 y2 plus so on Bn yn, with A belongs to F means field and x belongs to S. Then x plus y can be written as nothing but addition. So, within the set symbol A1 x1 plus A2 x2 plus so on plus an xn plus B1 B1 y1 plus B2 y2 plus so on Bn yn, and hence x plus y belongs to L of S. Also any A belongs to F, A belongs to F. So, here Ax can be written as A1 x1 plus A1 x2 plus so on an xn, and Ax belongs to L of S. Thus, L of S is a subspace of V. First condition, if x belongs to S, x equal to 1 into x, that implies L of S. Therefore, S is subset or equal to L of S. Second condition, W be a subspace of V. If L of S is subset or equal to W, then clearly S is subset or equal to W, since S is subset or equal to L of S. Conversely, suppose that S is subset or equal to W. If x subset or equal to L of S, then and x equal to A1 x1 plus A2 x2 plus A3 x3 plus so on an xn, x belongs to S and A belongs to F, F is a field, and therefore, x belongs to W. Since W is a subspace of subspace and x belongs to S is subset or equal to W. Thus, L of S is subset or equal to W. Third condition, if L of S equal to S, then S is subspace of V. Since L of S is subspace of V, conversely, if S is a subspace of V, then by 2 means then by second condition we proved this one, L of S subset or equal to S, and hence L of S equal to S. Fourth one, since L of S is a subspace, L of S is a subspace, we can write L of S equal to L of S. What is the set property? A complement whole complement equal to A we will write, or A dash whole dash equal to A we will write. The same concept here, space, previous knowledge. Next, fifth condition, S is subset or equal to T, that implies S is subset or equal to T, that implies L of S subset or equal to L of T by second condition. This completes proof of the theorem. Next theorem, this is also most important. Let W1 and W2 be subspaces of vector space V over a field F, then prove that W1 union W2 is a subspace if and only if either W1 subset or equal to W2 or W2 is subset or equal to W1. Proof, if W1 is subset or equal to W2 or W2 is subset or equal to W1, then W1 union W2 equal to W1 or W2. Suppose W1 intersection W2 is there, we will write W1 and W2. Here union means or, intersection means and respectively, and hence W1 union W2 is subspace of V. Conversely, suppose that W1 union W2 is a subspace. Suppose W1 does not subset or equal to W2, then we shall prove that W2 is subset or equal to W1. Choose x belongs to W1 such that x does not belongs to W2. Let y belongs to W2, then x comma y belongs to W1 union W2, and hence x minus y belongs to W1 union W2, so that x minus y belongs to W1 or x minus y belongs to W2. This completes the proof of theorem. Next theorem, this is also most important theorem for long answer type. Let W1 and W2 be subspaces of vector space V over a field F, and let W equal to W1 plus W2 that equal to x1 plus x2, x1 plus x2 such that x1 belongs to W1 and x2 belongs to W2. Then prove that W is a subspace of V, then W equal to L of W1 union W2. Proof, since the linear span L of S of any subset of S of V is a subspace of V, it is enough we prove that W equal to L of W1 union W2, since any element of X of W is the form x equal to x1 plus x2, where x1 belongs to W1, x2 belongs to W2, so that x equal to L of W1 union W2. Therefore, W1 subset are equal to W1 union W2. On the other hand, any element L of W1 W2 can be written x1 plus x2 etc. xn plus y1 plus y2 yn. Hence, x1 plus x2 belongs to W1, y1 plus y2 belongs to W2. Therefore, any element of L of W1 union W2 is of the form Z1 plus Z2. Z1 belongs to W1 and Z2 belongs to W2. Thus, W equal to L of W1 union W2, hence proved. So, definition V W1 plus W2 and W1 intersection W2 equal to 0. We say V is a direct sum of W1 and W2, and express this by writing V equal to W1 plus in circle W, binary operation. This is theorem. Consider the Euclidean plane which is vector space over R. Let W1 equal to x comma y, y equal to 3x. Similarly, W2 equal to x comma y such that y equal to x. Then prove that W1 and W2 are subspace of R square such that R2 equal to W1, binary operation W2. Proof, W1 and W2 represent two straight lines passing through the origin, and hence W1 and W2 subspace of R2. So, W1 intersection W2, then y equal to 3x, y equal to x, that equal to 3 equal to x, when it is possible x equal to 0. So, x comma y equal to 0 comma 0, 0 element of R square, therefore, W1 intersection W2 that equal to 0. Next, we shall prove W1 plus W2 equal to R2. Let x comma y belongs to R2 be arbitrary. Put a equal to 1 by 2 y minus x, b equal to 1 by 2 3x minus. Then a comma a belongs to W1 and b comma b belongs to W2. This can be written as x comma y equal to a comma 3a plus b comma b. That implies W1 plus W. Therefore, R2 W equal to W1 operation, hence proved. Next, let V be a vector space over a field F, S and T be subspaces of a. Then prove that L of S union T equal to L of S plus L of B. This is very important and simple. Since S is subset are equal to S union T, we get L of is subset are equal to L of S union T. Similarly, L of T is subset are equal to L of S union T. Hence, L of S plus L of T is subset are equal to L of S union T. On the other hand, x belongs to L of S union T. Then x equal to A1 x1 plus A2 x2 etc. An xn. Similarly, plus B1 y1 plus B2 y2 etc. Bn yn, where x belongs to S, y belongs to T, A comma B belongs to F, and hence x belongs to L of S plus L of T. Thus, L of S union T subset are equal to L of S plus L of T, and therefore, L of S union T equal to L of S plus L of T. This completes the proof of the theorem. Thank you very much.